we have done an RC circuit. We have done an LR circuit. So I think the only thing left in terms of these fundamental circuits is an LC circuit. That, of course, is a circuit that has an inductor and a capacitor, and we're not even going to put a battery in it. Let's just, what would happen if we just had this inductor and this capacitor staring each other down like that? LC. Well, let's apply Kirchhoff. I will rob him of one of his letters eventually. I think I've gotten it right so far. Kirchhoff loop. Well, okay, let's say the current is going that way. We want to loop that way. So we're going with the current through an inductor. Assuming the current is increasing, then you're going to get a back EMF. So we have minus L di dt. That's the potential drop across the inductor. And then here, current flows this way. Here's the positive plates. Here's the negative plates. And the drop across the capacitor doesn't depend on the current. It depends on the charge that is built up on the plates. So that's minus Q over C. So now I'm using little I for current, little q for charge. And we've gone all the way around the loop. So those are equal to 0. So right off the bat, we're in trouble. We have current as a function of time. We have charge as a function of time. And the current is already in a derivative. What a mess. So we know the way to get from one to the other is current is dq dt. So I guess what we have to do is write minus L d of dt of dq of dt minus q over c equals 0. And that is a second derivative. I'll go ahead and save myself a little space. This is minus L d2q dt2. So minus L times the second derivative minus q over c equals 0. All right, so now we just have to pull out our bag of differential equation tricks. Let's write it a little nicer and see if something comes to us here. We could isolate, usually in differential equations, you isolate the high derivative of the function d2q dt2 equals minus 1 over LC, comes over there, times q. That's where we are. And let's keep in mind that q is a function of time. We're looking for this function q. If we know the charge buildup in these plates, then we'll also know the current. We can just take its derivative. So we can find, I'll solve this for the charge buildup. We can solve it for the current. Doesn't really matter. But this is where we are. So we need to solve this differential equation for q of t. Our old tricks were maybe a substitution. Well, substitution is not going to help us here. Here's q and q all by itself. We would also put dq over q. Well, that's not going to do much for us because it's a second derivative. So it'd be d2q over q. Yeah, that's not going to work. So how to solve it? What do we do? Well, if you go in your freshman physics book, it doesn't really solve it. It just tells you the answer. Right? Maybe it gives you some physical intuition for why it does this, but it doesn't really solve it. Read the book carefully. It'll give you some circular argument about energy and try to trick you, but it doesn't solve it. So how do they really solve this in differential equations? Here is how they do it. I guess. You don't solve it. You can't solve it. How could you solve it? You can't integrate it because you don't know what it is. You can't solve it by integration. There are no tricks. You have to guess. Literally, you just make stuff up, and then you plug it in and see if it's true. If someone had told me that this is what we were doing when I took differential equations in 1991, I might not have gotten a D. But nobody told me that. I was very confused. But anyway, but don't worry, I retook it, and I got a C. Okay, so we're going to guess. So now, how do you guess? This sounds like you need experience and practice. Yes, that you do. You don't just get these mathematically, you guess. Well, you look at it, and you say, well, what function is equal to its own second derivative to within a constant? And you just start making up functions and see what you come up with. So let's think, what function do we know is equal to its own second derivative to within a constant? Well, 1 might be q of t would be sine, right? Sine, derivative of sine is cosine, derivative of cosine is negative sine. So it does get back to itself, sort of, when you take two derivatives. Another, well, if sine does it, cosine does it. All right. That's a function that's equal to itself, to its own second derivative, to within a constant. The derivative of cosine is negative sine, derivative of negative sine is negative cosine. And they even bring in the negative sign, how convenient. Another one is the exponent, exponential function. Derivative of e to the t is e to the t. Second derivative is still e to the t, sort of equal to itself within a constant. So the next step in differential equations is you plug them in and see if they work. So that's what we will do next. Let's plug in sine. So we're going to take our guess and plug it in. The q of t, now we're not just going to do sine. So I'm sure that was really bothering some people the way I wrote it. We want to write sine real general and with lots of constants so we can actually have it be a physics problem with units that work out. So we need an amplitude in front of the sine, a sine, and then we need something in front of time. We need a frequency. I'm going to call that omega t because we all know where this is headed. And we also, if it's a sinusoid, it's good to throw in a phase. I'll call phi. So our guess, our better constructed guess would be a sine omega t plus phi. So now, to plug it in, we literally just plug it into the differential equation. We need dq dt, and the derivative of sine is cosine. You pull out an omega, so it's a omega cosine omega t plus phi. And you need the second derivative. The derivative of cosine is negative sine minus a sine, and you pull out another omega, omega squared sine omega t plus phi. So now we're ready to plug in. So d2q dt2 was one of our equations, so that's minus a omega squared sine omega t plus phi equals minus 1 over LC times q, which is just a sine omega t plus phi. So basically, if this guess is correct, that has to be true. Okay? Well, you can see stuff cancels out. The sine cancels out. That's nice. This amplitude cancels out. The two negatives go away, become positive. And what this is telling you, the equation is talking to you. It's saying, you say, is this a good solution? The equation says, yes, if omega squared is 1 over LC. And you could ask the equation, what about a and phi? A and phi can take any value. So the equation doesn't care about a and phi, the amplitude and the phase. The equation only cares about what omega is. So good solution if omega is, we take the square root of 1 over LC. All right, so that works. Let's try another one. And you're thinking, surely he's not going to do the cosine. I mean, we just did, no. You're obviously new to the course, because now we're going to do q of t equals a cosine omega t plus phi. Therefore, dq dt equals a. Derivative of cosine is negative sine. Pull out an omega minus a omega sine omega t plus phi. And the second derivative, dq dt sine cosine. Another omega comes out, minus a omega squared cosine omega t plus phi. Now plug it in. Let's see. d2q dt2 is minus a omega squared cosine omega t plus phi. So that's the d2q dt2 equals minus 1 over LC, and then the function a cosine omega t plus phi. So you say, is this a good answer? And the equation says, well, yes, if this is true. So we cancel that, we cancel that, we cancel the a, we cancel the a, we cancel the negatives. And the equation says, sure, if omega squared equals 1 over LC. So that solution is good if the frequency of the function is the square root of 1 over LC, and the a and the phi can take any value. So both sine and cosine, perfectly acceptable guesses for this differential equation. We had 3 guesses, we might as well use them all. Let's try the exponential q of t, and we'll make it general. We'll kind of like the sinusoids, we'll put an a in front of it. E to the omega was what went in front of time, plus phi. Let's just stick that in there, because dq dt, well, the exponent just stays the same, but you pull down the derivative of this with respect to time, so it's a omega e to the omega t plus phi, and the second derivative, you pull just down another omega, a omega squared e to the omega t plus phi. All right, well, let's just plug them in. So the second derivative was a omega squared e to the omega t plus phi equals minus 1 over LC times q a e to the omega t plus phi. And we tell the equation, is this good? The equation says it's good if this is true, so the exponentials go away. Interesting. And the a's go away. Same thing. The equation says I don't care about the a and the phi, I only care about this omega. And it says it's good solution if omega squared is minus 1 over LC. Therefore, if omega is the square root of minus 1 over LC. But wait a minute. We know that L is going to be positive, and C is going to be positive, and 1 is positive. So we've taken the square root of a negative number. You can never take the square root of a negative number. That's an imaginary number. So we can't have an imaginary number in our solution. So that can't possibly be right.
It's actually right, but I'm not going to cover it, so just read about complex exponentials.
Okay, now that's our 3 solutions. This one is weird. We're going to stick with the sines and cosines. But the question is there another solution? I feel like there was, but I can't really remember it. So the question is there anyone that has the intelligence, the gravitas, the helpfulness that we all highly respect that could help me think of the next one? I'm trying to think who would know. Who would know? Oh, somebody is chiming in. Let's see if anybody knows. And it is Grove. Of course, Grove will know. And that final answer, of course, 0. Yes, 0 is the next guess that we could put in. Is 0 a function? Yeah, 0 is a function. Is it equal to its own second derivative? Sure. The first derivative of 0 is 0, and the second derivative of 0 is 0. So it follows all the rules. Is it a reasonable answer? Sure. Let's look at the circuit. Can nothing happen? Yes, that's a reasonable answer. It just sits there. That's often called the trivial solution. Of all the solutions you could pick, that one just is trivial, meaning it doesn't really tell you anything that's going on. So let's stick with the sines and cosines. So here's our circuit. We came up with 3 solutions to the differential equation that came out of Kirchhoff's loop rule. We came up with just that the charge can be 0. Basically nothing can happen. If we took the derivative, the current would just be 0. We came up with the charge on the plates is A sine the square root of 1 over LC t plus some phase. And we came up with that the charge could be A cosine the square root of 1 over LC t plus some phase. And if you wanted currents, just take the time derivative. This would become a cosine, this would become a sine. But let's just keep it in terms of charge for now. So let's plot these and see what the deal is here. So versus time, Q, the first one is just 0. Right? That's the trivial solution. Yes, the circuits can sit there and do nothing. Let's plot this one. So this one is sine. So at time equals 0, sine is 0. So it's going to do something like this, like that. And the next one is cosine. Cosine is maximum at time equals 0. So if we were to plot that, it would be maximum here, and you got to kind of line it up. It goes to 0 when that one is maximum, and it goes to minimum when that one's 0. I'm really horrible at this. Got to get them perfectly out of phase. There we go. That one's cosine. In the case of these two, they have any A and any phase. So what's strange is we have three solutions. It appears that we haven't really solved what this thing is going to do. It can do anything. And the reason is we haven't used any initial conditions yet. When you solve a differential equation by guessing, you get sort of a general solution. But to get the specific solution with the exact right function, you have to apply boundary conditions, or initial conditions in this case. So to get the exact answer, apply, in this case, initial conditions. So in this case, we want to think about this thing and imagine, okay, maybe it's sitting there neutral doing nothing, but if we could somehow grab the charge on this side and put it on that side and let it go and see what happens. That's kind of physically what we're thinking of doing. Perturb it and release it at time equals 0. So the way we would describe that mathematically is that at t equals 0, q equals q naught. That's how much charge we pulled and stuck on the top plate before we released it. And also I, which is dq dt, also equals 0. We're going to start it from rest and release it and see what happens. Okay? So we have two boundary conditions, one on the charge, or on the charge, the function, and one on the rate of change of the function. So let's apply this one first. So q at 0, we said, equals q naught. But if we plug that into the first guess, the sine guess, that's a sine omega t is 0, because this is at time 0. So that's a sine times phi. There we go. And now let's plug in for this guess. This is dq dt at time 0, so that would be derivative of sine is cosine. That would be a omega cosine omega t is 0, so cosine phi equals 0, right? Equals 0. Okay. So now we actually have two equations, two unknowns. We don't know a, we don't know phi. We don't know a, don't know phi. Don't know, but we have two equations. So this is the easier one to deal with. Something here has to make this 0. Okay? The amplitude can't be 0. That would be the trivial solution. Frequency can't be 0. That would be the trivial solution. So it must be that the cosine phi term is 0. Well, the only way to make cosine phi 0 is to make phi pi over 2, or 3 pi over 2, or 5 pi over 2, blah, blah, blah. Let's just make it pi over 2, just to make our lives simpler. And now, if phi is pi over 2, then we plug that in here. Sine of pi over 2 is 1. So we realize, oh, a is just q naught. So we just used our boundary conditions to find the real solution, which is q of time is q naught sine 1 over the square root of, or square root of 1 over LC, same thing, t plus pi over 2. That would be the real full solution. And of course, we're going to plug in guess number 2 and apply the initial conditions. So again, the initial conditions were that q at 0 equals q naught equals, this time we're using the cosine solution. So it would be a cosine omega t is 0. This is at time 0, phi. So q naught is a cosine phi. And then the other one, the derivative, the fact that dq dt is 0, would just be that, let's see, the derivative of cosine is a negative sign, pull out an omega, so minus a omega sine omega t is 0. We're doing this at time 0. Phi is still there. That equals 0. This is the di, the dq dt part. Again, two equations, two unknowns. So let's see, this is the 0, this is the one that we deal with. A can't be 0, omega can't be 0. We need sine of phi to be 0. And where is sine 0? Sine is 0 when phi equals 0. I hope you can tell my phi's from my zeros. Okay. So if that is true, then we plug 0 into here. Cosine 0 is 1. And of course, again, A equals Q naught. Pretty much the same thing we did last time. So what we get then, if this guess is Q of t equals Q naught, in this case cosine of the square root of 1 over LC t plus phi. I'm sorry, plus nothing. Phi is 0. Yes. 1 over the square root of LC t. So it looks like for the same thing we have two answers. So let's plot them. Here we go. Let's plot the cosine answer first. It's a cosine at time equals 0. Cosine is maximum, so it'll be Q naught here. That'll be the maximum value, and then it'll follow a cosine function. It'll go down and up, and go like that. So this is the cosine guess. Now let's plot the sine solution. See, the sine solution was also Q naught sine, this same thing, plus pi over 2. Okay? So at time equals 0, we just plug t equals 0 into a sinusoid, plus pi over 2. So that's really the sine at pi over 2, which is 1, which is the maximum. So it's actually here. It goes there. The sinusoid will keep going. Here, this must be when the cosine, when this thing is making pi over 2. Right? That's when cosine is 0 at pi over 2. Now, if we take that pi over 2 and add another pi over 2 in the sine, those together make a pi, and at that point, the sine solution is 0. If you keep doing this, you're going to find they're right on top of each other. We thought that we solved this twice, but we really didn't. We got one answer. There are not two answers. So if you have a system described by a differential equation, and you guess a solution, and you use boundary conditions to get the exact answer, there's only one solution. There can only be one solution because physically it can only do one thing. There has to be one mathematical solution that describes it. And here it looked like we found two, but they're really the same. It may look like two solutions. It's really just one solution. Okay? This is called the uniqueness and completeness in differential equations. If you find one, it fits, use boundary conditions, it is both unique and it's complete. So if you've never had differential equations, this may have given you an idea. Really, we're just guessing the solution. If you ever hear a mathematician say, we're going to construct a solution, right? That's their fancy way of saying guess. You may hear a theoretical physicist say, let's begin with the following Ansatz, right? Ansatz is basically German for guess. Ansatz is German for outset. So all they're really doing is guessing, so don't let them fool you.